Alright, it's time for free body diagrams. I love these things. Free body diagrams, that is our opportunity as physicists to show forth our artistic nature. That's right. Don't you laugh out there. Now, when you are doing a free body diagram, there are a couple of rules. One, your picture must be extremely lifelike. It has to look exactly like the object you're trying to, of course, talk about. So say, for example, we are going to draw a free body diagram for an airplane. An airplane, free body diagram, takes special drawing skill. Here you go. There's my airplane. Now that we have our airplane, we want to look at all the forces that act on that airplane. Now, if you take a minute, just stop and think about it. What forces are acting on an airplane? Well, we have the obvious, gravity. Gravity is acting on the airplane. We're going to draw that force of gravity acting on it, which we call its weight force. Now, technically, gravity is not a force. It's an acceleration. Everything, when it's in gravity, falls at the same rate as we learned in the last unit. So we call gravity an acceleration, not a force. But we have our airplane, our force vector drawn down. I'm going to label that mg. I label that mg because F equals ma, Newton's second law of motion. The force of gravity on the object is going to be equal to the object's mass times its acceleration. Its acceleration in this case is equal to gravity's acceleration, which is 9.81 meters per second squared, or g. So mg, I label that force vector right there. There are more forces than that acting on the airplane. We have a force obviously acting on it, holding it up in the air. And the technical term for that is lift. So we'll call it F sub lift. F lift. Lift force acting on the airplane. We have another force acting on it which causes it to go forward. And we're assuming that it's at cruising altitude here. So let's say it's an airplane at cruising altitude and cruising speed. It's not speeding up, it's not slowing down. That means that all forces on it are equal in magnitude in all directions. There are no net forces acting on it. So if there's a jet pushing it forward, there must be something also pushing back on it. The thing pushing it forward we'd call thrust. So I'll put F sub thrust, and then the force pushing back on it, and I'm trying to draw these arrows equal in size because they're about equal magnitude, obviously. And this one would be F drag force. That's the wind resistance on the airplane, they call it drag. So, here's our airplane. We analyze the forces that are acting on it. Gravity pulling down. Lift, caused by the wings, pushing it up. Drag, which tends to try to slow the plane down. And the thrust of the jet engines, which keep it going. You add all those forces up and you get constant motion in one direction. Newton's first law of motion, law of inertia. If all forces are balanced, then the acceleration on the object won't happen. It'll keep in its constant state of motion as long as there's no net force acting on it. So, there we have our free body diagram for an airplane. Now, next we will let's draw a free body diagram for let's say a rock. We're going to draw our rock. There you go. Handy dandy rock. Love it. What are the forces acting on the rock? Well, it's on Earth. mg, weight force. mg, or the weight force, always acting down on an object. There might be other forces acting on it too. Let's suppose that the rock is just sitting there. There's nothing pushing it to one side or the other. Are there any other forces besides gravity acting on it? Ah, I heard you there. Doesn't feel like I'm on Blue's Clues here. I'm waiting for you to respond. Anyway. Yes, there are forces acting on it. Obviously, it's not falling down, right? If it's not falling down, there's something holding it up. The force of the earth holding something up, we call it N. We use N because it's short for normal. We call it normal force. That's the force that a surface exerts on an object to hold it up. Normal force. It's a contact force caused by anything that holds anything up. Could be the ground, could be a table, could be the chair you're sitting in, whatever. So N, my normal force, and my weight force. And as far as I can tell, since we're not talking about wind or anything else, there's really no other force acting on the rock. So our free body diagram for a rock just sitting there, we have the normal force of the ground pushing up on the rock. We have the weight force of the mass of the rock being accelerated by gravity. And there you go. Those are the forces that act on a rock. Real challenge now. Let's see if I can draw a dog. Dogs are more tricky. So I'm going to draw the best dog that I can. Yeah, absolutely. Oh, I've got to be more particular. So I have my dog. And my dog, let's stage this a little bit. Our dog is going to be just starting out on a run. So it's accelerating, it's speeding up. Starting out on a run and going after a car. Dog just barely starting to accelerate. What are the forces acting on that dog? Well, as always, we're on Earth. We have our weight force, mg, acting on the dog. If we think about it a little bit more, well, the dog isn't falling through the ground. Since it's not falling through the ground, it means the ground must be holding it up. That force that we talked about just now, we abbreviated N, or the normal force, must be acting on the dog, holding it up. And what other forces? The dog's accelerating, we know that. So there must be an unbalanced force, or a net force, acting on this animal. So, whatever we want to call that force, going in this direction, we'll call it F, force of the dog. Okay, the dog's run. So the force of the dog. This direction, we really don't have a force acting on it that we can label. There might be some wind resistance once it gets up to speed, but when it's just starting out, there's really nothing that we can label on there. There's nothing that we can put our fingers on to say that there's a force acting on it, unless we, of course, say that there is, like a rope tied to the dog's tail or something, but there's not. So, we have our dog, gravity force pulling down on it, normal force acting up on it, about the same size, and then the force of the dog running as it tries to speed up. And nothing on this side. So if you look at this, and the reason we like free body diagrams now, if you look at this dog, and you look at the arrows, you can tell the acceleration is going to be in that direction. It's going to accelerate that way. Because the force, the net force, or the unbalanced force acting on the dog, is in that direction. These are balanced, so it's not going to go up or down. There's nothing holding it back, so it's going to go that way. And that's how these free body diagrams work. If you have any questions, bring them to class.